Hello everyone. In this video, I'm going to walk you through some of the R codes that shows you how to do logistic regressions. I hope this script will help you understand how this regression works, especially in an empirical setting, and how to do some of the basic and the most essential computing when it comes to logistic regression. So let's start by looking at the first part of the code up to this point, up to lines 30. So what I'm doing over here is that I'm clearing the environment, setting the seed for reproducibility. And then what I'm doing is that I'm creating 10,000 data points spread evenly between -3 and 3 for a predictor variable. Then I am using the logistic function to transform these values into probabilities. This is the formula, 1 upon 1 plus e to the power negative this expression. The 0.5 over here is the intercept and 1.5 is the slope parameter. Finally, I'm using this R binom function to generate random binary outcomes 0 or 1 based on these probabilities. Each observation has a probability of being 1 based on the logistic function that we define. Next, I'm going to estimate the linear regression models. I'm going to regress y on x using the ln function and store the results in lin_model. Then I'm going to create the predicted values of y using the predict function and store them in lin_pred. Then I'm going to fit a logistic function over here. The only difference between LM and GLM is that GLM stands for generalized linear model. We regress y on x and then we specify the type of generalized linear model, which in this case is logic. And then we create the predicted values using the predict functions. And the type equals response in the prediction gives us the probability rather than the log odds. And then I am setting up the canvas and then plotting them and adding some lines. So if I run this whole thing up to line 69, and we now have that figure. So this is the figure that is there in the slides, and the codes over here generate that. And as you can see, this is the problem with the linear model. You can have predicted probability that are negative and exceeding 1, which doesn't make any sense at all. So the next section of codes will demonstrate how the logistic function changes with different parameters. So I start with a clean slate. I define a logistic function which will take in 3 arguments, x, beta naught, and beta 1, and it will return a probability value. And I am trying out 3 different versions of that. And when I plot, I get these functions. So depending on the parameter that I've set, I can get different kinds, like same function, just of different forms. And this is also what is there in the slides. Clearing up the canvas. So now let's move on to a more comprehensive example. I'm going to work with the simulated data with multiple predictors. I'm going to set the sample size at 10,000. I'm going to generate 5 predictor variables, x1, x2, x3, x4, and x5, and I'm going to give them different I'm going to draw them from different distributions. And the way I'm trying to construct it is that x1, x2, and x3 actually matter for the outcome, but x4 and x5 are absolute garbage. And I do that by assigning the related true effects of x4 and x5 to 0. So this is really interesting because we are explicitly setting x4 and x5 to have no effect by setting the coefficient to be 0. These are noise variables, which is realistic in actual data analysis because often some of the predictors that we think are useful actually turn out to be irrelevant. And then we calculate the log odds ratio and then we convert it into probability using the logistic function and generate binary outcomes based on that. So these lines of code exactly follow how the logistic regressions work. So we have some zeros, some ones, but an easier way to do that is of course using the GLM function. So first I combine all the variables into a data frame and I check for the proportion of positive cases for the binary outcome and we get a number 0.1319. So 13.19% of the cases are positive. And then we split the data into training and testing. I'm going to keep 70% of this data at random as training data, the remaining 30% as testing data. So I set that up. So my training size is 7,000 observations, testing size is 3,000. And then I build the logistic model using the GLM function and I summarize it to look at the point estimates. As you can see that x1, x2 and x3 are considered to be relevant and they have a statistically significant relationship. But because we mechanically set up x4 and x5 to be redundant, they do not have any statistically significant relationship with respect to y. And then we calculate the odds ratio by taking the coefficients and raising it to the power e, like e to the power that coefficient. So that gives us the odds ratio. We can calculate the confidence interval. We can also create a table using the cbind options where the coef table will have the point estimates, the related odds ratio, and the confidence intervals. Now, let's move on to the model evaluation. So we want to see how this model performs on a data set that has not been used for building up this model. So we regress this model on the test data, get the predictions. We need to load some packages along the way. And then we have the confusion matrix details. So confusion matrix spits out the accuracy, which is probably one of the basic things to look at. 0.875 means 87.5% of the times our predictions are correct, which is a pretty high number. And we can also calculate the true positives. Like we can also get a summarized version of the confusion matrix by using the conf matrix $table, and we can print that over here. And using this table, we can generate the other key metrics. So we can generate the true positive, which is nothing but the second row, second column, true positives. False positives is second row, first column. So true negatives, which is the first row, first column. And then the false positives, false negatives, which is the first row, second column. So we can get all of that from this confusion matrix tables. And then we calculate the accuracy, the precision, the recall, specificity, and F1 score. So we run these lines of code and we have a result. So our accuracy is 87.5%, precision is 51.9%, sensitivity is 14.2%, specificity is 98%, and F1 score is 22.36. These are different statistics that you can extract from the confusion matrix table to get a sense of how accurate your predictions are. And then you can also create that AOC, our EUC curve. This should not have happened. Okay, so there were some issues in the previous screen. So it took me some while to debug, and I'm going to start again from the EOC and ROC and EOC graph. So once I have the model, I have the test data, I want to calculate the ROC, and from there I want to calculate the AUC. And so this is the code that does that. It is, so the ROC function takes two arguments. First is the response variable, which in this case is test data $y, and then the predicted probabilities. And for whatever reason, this can be a package issue or something else. It's not letting me run this function independently, so I'm using this command where I'm explicitly telling R to use this function from this package. So ROC function comes from the PROC package. So name of the package, ;; function name. So that's the format. So once I have that, I have the ROC. So it is an object that takes in all these different entries. At this point, it's not super important to understand that, but the most important thing over here is the area under this curve, and that we get to be 79.67%. And this means that 79.67% of the times we are able to accurately measure our predictions are accurate. And this is a good number. In good models, we typically see values between 0.7 and 0.9. If it is 0.5, then it's as good as random guessing. If it was 1.0, then it could have been perfect, but we do not get 1.0. So this is a number. So next up, what we are going to do is we're going to investigate different thresholds. So till now, I've assumed that if the predicted probability is more than 0.5, I'm going to give the predicted status as 1. But that's kind of arbitrary. So now I'm going to set different thresholds, redo this whole analysis, and see what results I get. And what I get is that I have some variations in my accuracy for different levels of threshold. Obviously, as my threshold increases, my accuracy increases, but my precision kind of takes a hit later on. So there's a trade-off there, because I have to balance between type 1 and type 2 error. So higher is my threshold, one type of error, the chance of committing one type of error goes up, and the chance of making the other type of error goes down. Next up, we are going to look at the model diagnosis and influential observations. The code is pretty straightforward. So we have 571 potentially influential observations over here. It's a number, and we use Cook's distance that we have already done in an assignment to look at that. And then we are going to look at the pseudo R-square using, and for that we need the desk tools package. So we are going to install that. And then we're going to use a pseudo R2 function which can generate different versions of the pseudo R square, whether it's McFadden, Cox-Snell, Nagelkerke, and other measures. So I'm going to run this command, and we have that. So if you're using the McFadden's measure, our pseudo R square is 0.19. For Cox-Snell it is 0.14, Nagelkerke is 0.26, Fischer is 0.17. Because this measure is calculated differently, the numbers will vary, but overall they're pretty consistent. And these are generally good numbers as far as pseudo R square is concerned. So this is the video for running logistic regressions, different aspects of statistical learning using classification models. I hope this was useful, and if you have any questions, please do let me know. Thanks.